We have had the opportunity and benefit of working on many passive house projects, whether it be directly in the greater five boroughs or directly adjacent to, as well as all over North America and globally. And we take a lot of pride in our capacity and ability to do so. So really what I'd like to do today is just briefly discuss what thermal breaks are, their various applications as a whole, and really just go over them at a high level. Really, as a manufacturer, we take a lot of pride of having every project get treated as its own delegated design. So far as we tell designers, design the way that you're really looking to design your structure. Um, and then we can really, figure out the thermal breaks from there. Yeah, there are some considerations to take into account, but really design the way you want to design, and let the manufacturer assist and help facilitate with those solutions on their end. So as far as who we are as an organization, we have offices in 14 countries, with sales in 34 countries now. We have over 1,000 employees. We've been around for over 60 years. We just celebrated our 60th anniversary last year. And our company's founder, Eberhard Schuck, was actually the inventor of the first commercial thermal brake. So many decades ago, about 45 years or so ago, he had, um, during a vacation, noticed condensation at a balcony connection during the winter where he was in Austria. And as an engineer by background, thought, why could that be? Lo and behold, obviously, we know it now to be due to thermal bridging. But that's what really prompted him to say, okay, here is a problem. What is the solution that we can come up with to that end? And since then, over those 45 years or so, we've installed more than 16 million thermal brakes globally. In addition to thermal brakes, which is what most people know us for, we also manufacture punching shear reinforcement like stud rails, shear dowels, various facade attachments like fiberglass, glass reinforcement fiber, uh, as well as sound insulation and expansion joint. The learning objectives about this course really are why, how, and where thermal bridging occurs, and the three primary issues that are associated with thermal bridging, why it's more important now than ever to address thermal bridging. A lot of people will say, well, we've been constructing the way that we've been building for however many decades. Why is this suddenly an issue now? Uh, and then how do we go about incorporating those thermal breaks into our designs? And as I mentioned, we go about designing in a conventional manner, and then we just put a little twist on it, so to speak. And then really what you should look for when you're designing, in terms of services and solutions that the manufacturer should be providing you. So as far as an industry overview is concerned, um, and this study is from a number of years ago, actually, so consumption has gone up considerably, but we're waiting on the latest facts and figures. But the US energy consumption alone was over 40 quadrillion BTUs. So we know that that's obviously a large number. But if we set that number aside, we really see commonality at the top of what the largest consumers are of our energy, for both residential and commercial sectors, and that's clearly with space heating. And so it's how can we make the largest impact through um, our energy consumption? And so we look at the highest line there, the space heating, and then we know, okay, well, perhaps if we design more efficiently, more effectively through both our building envelope and our mechanical systems, we have the ability to reduce that consumption and thus be more efficient overall. So in conventional older buildings, they were poorly insulated. There were not great building materials so far as efficiency is concerned. We have a lot of older mechanical systems, a lot of single pane windows, again, poorly insulated. So you would have to really rely on a higher ambient air temperature to maintain a relative level of comfort for the occupants within a structure. And there's great variability amongst the various building materials in those older structures when contrasted against that internal air temperature. When we're talking about more modern structures with those more efficient materials, that tighter building envelope, they're obviously well insulated. And so you're able to rely on a much lower internal air temperature to have a more comfortable atmosphere for the occupants, whether it be residential or commercial. So it's through the combination of those more efficient materials, more efficient mechanicals, and then having to rely even less so on those mechanicals due to those more efficient building materials and design approach that we're able to reduce our energy consumption from what it historically has been. So, why is it important to address thermal bridging now? Again, people going back, many designers with decades of experience will say, again, we've been building this way, we've been designing this way for decades. Why suddenly now thermal breaks? And that really comes down to the tighter building envelopes that we are having now with those more efficient materials. So the tighter building envelopes are really holding in that humidity, especially when we are talking about specifically about passive house, and really maintaining that tight seal everywhere throughout the structure. Um, and so that's where relative humidity is going to come into play above all else. And when we have that high humidity level on the interior, meeting that cold surface, that's where the condensation really is going to have the ability to proliferate the most. And so that's where we want to make sure that we minimize and mitigate these weak points within that envelope as a whole. So yes, we're, looking about triple pane glass and various ways that we're making our envelope more efficient as a whole. But really what that's doing is also putting emphasis and even greater focus on the weak points in our structure and the ability to have that condensation, really build from the interior humidity with those tight seals that we have. So as far as thermal bridging in our structures goes, what does thermal bridging do? And it's effectively as simple as it sounds. It's a bridge, it's a conduit for thermal conductivity to occur. So it offers that easy path for the warmth and the cold to transfer through our conventional building materials. And as we know, steel and concrete are fantastic mediums for thermal conductivity. Obviously steel, but concrete is no slouch either. It's a fantastic conductor of thermal transfer. And so any point where we have that continuity of whether it be a balcony, a parapet, a canopy, all of those, if they're not appropriate insulated, and conventionally they have not been over the many decades, that's really where the weakness lies within our envelope. So yeah, we might be having very high R value insulation. We may be having, again, very high R value glass and design and very tight seal. But if we're not addressing the design holistically and those weak points, then that's really going to have that emphasis and really create that focal point for the thermal conductivity and the condensation to ultimately occur. And so what do thermal breaks do? Again, as simple as it sounds, it's going to put a break and significantly reduce that thermal transfer through those weak points of our building envelope. So it's not going to entirely mitigate it, but it's going to significantly reduce it. And really what we're trying to do is get it so we're having those interior temperatures above that dew point, that condensation point, and thus also having less energy transfer through those weak points and needing less reliance on our mechanical systems and less energy consumption as a whole. So just comparing and contrasting thermal transmission through various materials, we can see structural steel on the right um, as being many, many factors above our insulation, our wall insulation that we would conventionally have, even gypsum board and brickwork. Um, it's really the largest medium where clearly heat can easily transfer through it. One thing that I just want to point out here is the comparison between conventional structural steel and stainless steel. While stainless steel still clearly is a very high thermal conductor itself, it has a third of the conductivity that conventional structural steel would. So, what we look to do as an organization is at the end of the day, our connections are obviously structural in nature. We need to make sure that the balconies still stay attached appropriately. We need to make sure that the parapets, the canopies, everything is structurally sound. As it's inherently designed by nature. But what we look to do is we look to incorporate stainless steel for our reinforcement rather than conventional mild structural steel. So we get a reduction right off the bat just by changing the materials to that end. We look to take it a step further by blending the stainless steel with other various metals that allow us to further reduce the profile and increase the strength of the metals that we're using. So we're actually having less of a surface area as well, in addition, for that thermal transfer to occur through as well. And then right behind the structural steel, you'll see the concrete, and that's about a tenth of the stainless steel. Uh, however, it still is a fantastic conductor and really, especially in the greater New York City area, that's what we come across the most is the continuous run of concrete being poured monolithically in a continuous pour from interior to exterior. Um, and the ability for us to mitigate that transfer by incorporating the thermal breaks. So a lot of people think, okay, steel, yeah, we know about steel, but again, concrete, while it is a fraction of the steel itself, is no slouch itself, and generally speaking, will have a significantly greater profile than structural steel, so you have that much more surface area to act as that conduit for the thermal transfer to occur. So what are some of the problems caused by thermal bridging? So as I had mentioned previously, we know obviously that's where the thermal transfer is going to occur. And as we're designing and constructing these buildings with tighter envelopes as a whole and maintaining that higher relative humidity. Again, what that's doing is we're having those cold surface areas with that high humidity and having the ability for the condensation to occur. And with that condensation, we know that there are some issues that are associated with that. As that wet dry cycle continues to go over time, generally mold, um, gypsum board, drywall is a fantastic organic material for mold to proliferate through, quite frankly. And uh, generally speaking, it's hidden. And by the time it presents itself in a physical manner, it has manifested significantly. where it cannot be seen by the walls, by the eyes, excuse me, thus resulting in significant remediation costs that would far exceed the cost of incorporating thermal breaks in the first place, on top of health issues, potential lawsuits, just the sheer inconvenience that occupants would have by having to go through the remediation work in the first place. Even though building design has evolved over the years, where we've gone from a lot of perpendicular straight lines and 90-degree angles to beautiful curvature, if we don't address the problem as a whole, even though our designs have updated, if we if we don't do something about the root cause, then again, obviously that's going to persist as a whole. So if we contrast, old balconies from the city from the 1950s versus modern skyscrapers of the last decade, they're no different. We're talking about the same medium, the same materials, the same issues occurring. So it's really about getting to the root cause of what those issues are. And so the example that we really like to make here are twofold. We have one of the motorcycle. A lot of people relate to the motorcycle and having an air-cooled engine for the motorcycle, as well as for the motherboard or the internal parts of a computer, where effectively you have what are known as cooling fins or heat sinks attached to these items, whether it be, again, a motorcycle engine where internal combustion is occurring and an explosion is creating heat. And how do we dissipate that heat? Well, we have these cooling fins increasing the surface area on the outside of the motor. So as we're riding our motorcycles down the highway, uh, that cool air is going to pass over those cooling fins, and that the metal of that engine is always going to look to maintain balance or homeostasis as much as possible. So it's going to draw the warmth of that internal combustion explosion occurring on the inside outward to where it's cooler and continue to dissipate the heat. And it's the same thing with our computers, where we have our heat sinks of there's a heat generated by our computers, obviously, as we all know. They have cooling fans, but they also have these heat sinks that are shown on the right-hand side of the slide, where, again, it's all about that surface area and having that high surface area to volume ratio where it lets that air flow through and subsequently allows the dissipation of the heat to occur. And it's no different with our building envelopes themselves. So we think about these cooling fins as our balconies, our canopies, our parapets, all of our various connections. It's all tied to that inner diaphragm of the structural nature and support of the building itself. And we want to separate the two as much as possible so that we're not pulling that heat, that energy from the inside and just having it be lost to the outside, where, again, it's basically money flying out the window. So here we show, just some of the effects on the overall building envelope of having just your exposed balcony versus a balcony with a concrete thermal break. Um, and so what we're able to do is effectively use less insulation to achieve an even greater R value as a whole of our wall makeup or our wall envelope. Um, so conventional concrete thermal breaks would be about 3 inches wide. And really what you can see is even if you were to do 3 inches of extruded polystyrene with an R15 R value and pour through, your effective R value is still going to be less than that of a thermal break assembly with a 1 inch extruded polystyrene. So you really, if you ignore the problem or you design around the problem, that obviously doesn't make the problem go away. And it's not going to make the issue of the condensation in the mold go away either, because, again, it's going to really point focus it on those areas of weakness. And so, being the energy efficient company that we are, we like to relate everything back to nature ultimately at the end of the day. And so, we always use this example of the penguins, and we say the penguins are our buildings. And so, they have a nice surface ratio. Um, in terms of their total area to the volume. Their blubber will act as their insulation. Their skin will act as their air vapor barrier, and their feathers will act as the rain screen. So, where do we have the potential for the heat loss weakness within the envelope of the penguin building, if you will? And so a lot of the common answers that we get are the beak, the eyes, the wings, and they're all great, thoughts and answers. Ultimately, the wings can be tucked against the body so they can help maintain heat to that end. The beak is cut off on its own, and the eyes they're able to conceal. But really, the answer ultimately lies within the feet themselves. And so the penguin feet actually have a natural built-in thermal break. So the primary circulatory or blood system of the penguin will run down to the penguin ankle, if you will, as we affectionately call it, and then circle or cycle back up into the body. And then what they do is they actually run the least amount of blood flow through their feet as possible, effectively just keeping them functional, attached, comfortable, but not where they're going to get warm, where they effectively melt ice. And if they stay in one spot too long, then they're going to become penguin popsicles. And so it's the same premise with our products, or thermal breaks, I should say, as a whole, as we incorporate them into the structure. So when I showed this slide previously without the thermal break, the surface temperature was 52 degrees Fahrenheit under this model with a conventional 7-inch concrete to concrete thermal slab with a 32-degree Fahrenheit exterior, 70-degree Fahrenheit interior temperature. By incorporating the thermal break, we're able to get that interior temperature up by approximately 11 to 12 degrees Fahrenheit. And what that does is that actually gets us up over the condensation point for our geography in the winter with these conditions. It fluctuates a bit, but it's generally around the 56 to 58 degree Fahrenheit range. And so without the thermal breaks, clearly we're several degrees below that condensation point. With the thermal break, then we're able to get well above that condensation point and thus not have that be a concern or a critical factor for us in our design. Now, on top of that, we have two other benefits. We obviously have the energy efficiency benefit where we're losing less energy or using less energy to heat our space. And we also have the user occupancy comfort component as well, which is a bit hard to quantify because there's no direct number obviously associated with it. But over my 7+ years of the organization and dealing with many occupants, I have designers who obviously live in the city, whether it be architects, engineers, building envelope consultants, or contractors, general contractors, concrete contractors, steel contractors. It's funny having those conversations with people where they talk about where, yeah, they feel the cold at the perimeter where they have these connections for the first few feet within to their living space. And obviously they don't have thermal breaks as they make this reference. And so really what the thermal break does is it really helps to mitigate that feeling of that coldness within our livable area and maximize the space that we have. Let's face it, ultimately New York City we don't necessarily have the benefit of the most amount of square footage in our living spaces, and so we really want to make sure that we maximize it and have that comfort for our occupants to the fullest and greatest extent. Now, additionally, something that's come into play has been the updates to ASHRAE and the addendums, where more and more people are calling for the continuous use of thermal breaks at balconies, parapets, anywhere where we have a penetration of our building envelope. And so the New York City DOB code has done a nice job of incorporating that as well. So we're not having these weak points within our structures. So about the thermal breaks themselves and their applications, um, the most common areas where we find thermal breaks, again, are going to be our balconies, our parapets, our canopies, and our, what I will say is a slab edge, but effectively what it is more of a faux slab edge as an architectural element, where we have a thermal break about 6 inches inboard of what that exposed architectural slab edge finish would look like as it's shown in the picture on the right. There are obviously other applications as well, but those are the primary ones. And I would say far and away, the one that we come across the most or work with the most are the balconies themselves, and that's what most people will know us for. And so just showing an isometric view of, with a cutout of the balcony thermal break and how it works is it falls in plane with our building envelope, and it has the structural steel already incorporated through the insulation of the thermal break. We just make the tie between our interior reinforcement cage and our exterior reinforcement cage. And then the thermal break just does the rest. It structurally ties the two together and then significantly reduces that thermal conductivity by about 3/4 as a whole in the concrete applications. Excuse me, actually up to approximately 90% in the concrete applications. The steel applications, which I'll touch on momentarily, are the ones that's about 3/4. So here we just show an isometric cutaway of the concrete to concrete thermal break itself and its components. So we have the gray insulation through the middle of the assembly itself. On the top and the bottom, we have a rigid PVC cap that encapsulates the cementitious fireboard that gives us a UL fire rating. Clearly, you can see the steel reinforcement that runs through. So we have both the tensile bars that run through the top for tension, and then we have the shear bars that dive down or dip to the bottom of the thermal break assembly and then come back up and then develop, make a 90-degree angle, and then develop back out as well. And then in addition to that, we have what you will see are blue blocks placed sporadically through the bottom of the concrete to concrete thermal break. So there are three forces that we're looking to transfer through the thermal break assemblies. We have tension and compression working together. So that's where we have our tension reinforcement bars, and they work in tandem with those blue blocks in the bottom, which are our HTE, which just stands for high thermal efficiency compression modules, and those two will work in tandem. So as we have our balcony and gravity wants to pull it down and our occupants standing on it want to push it down, you're creating tension along the top and you're creating that compression along the bottom. And then the third force that we want to resist is shear force, and that's effectively just dropping straight down. So you have what's known as a bending moment with the tension and compression, and then you have the shear force, which is just gravity pulling directly down. So that's where you have those three primary structural elements that are incorporated into the thermal break. One last thing that I want to point about it is if you look closely at the steel reinforcement through the center of the thermal break itself, you'll see it's a lighter gray, silverish reinforcement or rebar. and then it transitions to a darker, dark gray reinforcement. And what you're seeing there is actually stainless steel through the middle of the product and standard mild steel on the extremity or the development of the reinforcement itself. And so if you'll recall from one of the earlier slides, the stainless steel has about a quarter of the transmission that the standard mild steel does. So that's why we incorporate stainless steel as really that primary connection. Sorry, one of my coworkers with their toy. Stop. Thank you. Sorry about that. Um, that's where we have why we have incorporated the stainless steel through the center is really to reduce that thermal conductivity as a whole, as I had mentioned, while still maintaining the structural nature of the product, which is arguably the most important, because if it doesn't stay attached, to what good is the product in the first place? And then in addition to the reduced thermal conductivity, stainless steel obviously is not going to corrode. So when we introduce a concrete to concrete thermal break, we're also allowing two cold pour joints, one on either side of the thermal break assembly itself. So let's just say hypothetically, if rain or water were to ever make its way in that cold joint, that's another reason for the stainless steel as well. It's not going to corrode over time like conventional mild steel would. A question I get a lot is why don't we just use stainless steel all the way through? And the short answer for that is cost benefit analysis, where we get the thermal performance that we really need from having the stainless steel stick out 6 inches on either side of the face of the insulation, and then transitioning back to standard mild steel. Now, we do also have products that, rather than incorporating steel, use glass fiber reinforcement as well, where that will reduce the thermal conductivity even more. Um, but not everybody is quite ready to accept thermal breaks in the first place. As I mentioned, many people have been designing the way that they've been designing for many decades. So thermal breaks as a whole is a large adjustment for them in the first place. Glass fiber reinforcement at a balcony is even more alien to them. So we do have the option for both. But 95+% of the applications incorporate the steel reinforcement, and a very small percentage incorporates the glass fiber reinforcement, although that is slowly growing over time. Now, regarding the concrete parapets themselves, where conventionally many designers will just, do extruded board and wrap up and over, the benefit of incorporating the thermal break at the parapet is obviously we're talking about less materials being used, as well as less labor being involved to actually wrap that parapet wall as a whole. In addition to that, even when you wrap the wall, the warmth from the inside of the structure is still going to go all the way up into that full height, that full projection of the parapet. Whereas when we cut it off at the roof line with the thermal break itself, then we actually have an even greater reduction of thermal transfer because we're not heating that parapet wall as a whole as well. Even if it were to be, wrapped, again, it's still going to draw the heat. Heat's always going to want to rise, and it's just going to draw that heat from that roof pour itself. So by cutting off the parapet at the roof line, it does an even greater job of what a wrapped parapet would do as well. Now, I touched on canopies and, steel to steel connections, but there also is the marriage of the two, where we have concrete to steel connections, where we might have, and generally more often than not, it's going to be a concrete structure with a, steel canopy, steel balcony, something that gets bolted on, attached to after the fact. But it could be, quite frankly, the inverse, where we're bolting to a steel structure, and it could be a precast balcony, it could be a precast canopy, it could be obviously something that gets cast in place on site. That happens less often, but it does happen. And so you do have the ability to incorporate these concrete to steel connections as well, whether it be steel on the inside or steel on the outside. And then to take it a step further, back to the steel to steel connections that I had mentioned. So here we're just showing both the canopy connection with a steel to steel, as well as a large roof overhang with a steel to steel connection. And really the nice thing about the steel connections is all that's happening there is, rather than having a steel member run continuous from the interior to the exterior, you're stopping that continuity, you're introducing a head plate on either side of the steel member, and you're just putting a thermal break block in between the two and bolting them down. So the product already comes with the threaded rod and the nuts already part of the assembly. Those threaded rods just go through the predetermined holes of the head plates on the steel members. They get torqued to the appropriate tightness on site, and your thermal brakes have been installed for a steel to steel assembly. So it's nothing that any steel installer or subcontractor, contractor in the field hasn't come across before. They all marry head plates together. It just happens to be we're introducing another head plate as part of the design, and that's going to significantly reduce the thermal transmission, the thermal conductivity that goes from the interior to the exterior of the structure. And so actually showing this as a profile, we would have what would be a continuous beam on the left, a continuous I-beam, but it would be the same theory or premise with a hollow section steel tubing as well. Clearly, the end plate itself significantly increases that surface area, but what the steel to steel thermal break connections do is they actually have a very small profile of steel that goes through the assembly itself, as shown on the right hand side. So yeah, those end plates might be large, but ultimately the profile of steel that is going through the our thermal break connection is going to be significantly reduced to that of what a continuous beam would be. And so as we contrast that against thermal pads, really thermal pads, unless they're a minimum of 3 inches, they're actually, because you're increasing your surface area, they're actually going to increase the amount of thermal conductivity that's occurring as shown on the previous slide. That end plate, if you put a pad in there, you have a much larger surface area. And so that's what pads are going to do, where the steel to steel thermal break assemblies are going to significantly reduce the amount of area that gets transferred through. So as far as design and installation goes, the concrete to concrete thermal breaks, they just get dropped into the formwork on site, and you build your rebar cages up to the face of the thermal break assemblies. So any concrete contractor can install them. There's nothing special or new that's associated with it. They're used to building rebar cages, and it's going to be the same thing with installing thermal breaks. We're just building the cage up to either face of the thermal break assembly itself. So just showing you some pictures with some various, here's within slab ducts. We don't deal so much with it here on the East Coast, but again, you design the way you want to design and we can work around it. This is just showing various steel to steel, concrete to steel connections on site. So again, rooftop dunnage is a component, but all different ways that we can incorporate it. Post-tension slabs are something that we come across very commonly. So whether it be cast in place, conventional, or PT slabs, we can incorporate thermal breaks. Design the way you want to design, incorporate the supplier, and we can go through and come up with the appropriate solution. So really, in the tail end here, we just, really want to impart with everyone that your partner should be able to help provide clear installation instructions, provide CAD, BIM files, have expertise and support, be able to walk through everything with you in an iterative step-by-step process, and provide stamped and sealed drawings. So as I mentioned, this gets treated as a delegated design. You just hand your design off to the manufacturer, and the manufacturer will do the calculations, the takeoff, and then ultimately get that all stamped and sealed. So in summary, thermal bridging occurs where balconies, parapets, canopies, any sort of penetrations to our building envelopes occur. There are the three issues that are associated with it, which is the condensation, the heat loss, and the thermal comfort, the occupational comfort, if you will. Incorporating the thermal breaks really allow you to mitigate and alleviate these three issues. And you should expect your partner, your provider, to clearly and efficiently be able to assist with any facet of the design process with you. And so just for the last minute or two here, some North American references. The first project that we ever did in New York City was finished in 2012, Chelsea Green down in Chelsea Market. And since then, we've done over 1,000 projects in the greater New York City metro area. So it's really taken off by leaps and bounds. Since this first project in New York City. Our first project in North America was actually way back in 2002 in Cincinnati at the Contemporary Museum of Art. But yeah, our first one in the city here was with the Jacobs Group, WSP, and Turner Construction. Really what we want to alliterate here, show here, demonstrate here is design the way you want to design, and we can work around it, whether it's a radius bend, a straight line, whatever it is. Have a conversation with your provider, your partner, about what you're looking to design, how you want to design it. And generally speaking, there's going to be a solution to that end for it. One cool project that we like to show off, and we're still waiting on the actual photos of it in place, but we did thermal breaks for the new King George Island station down in Antarctica, where we thermally isolated the structure itself from the steel supports that go down and hold the structure up off the permafrost there. So having said that, I thank everybody for their time. Hopefully it was, worthwhile 50 minutes or so for everybody. And if you ever need anything at any point in time, please don't hesitate to contact us directly. This particular slideshow has my counterpart Allison's contact information there, but I think Andreas, we also shared mine as well. So I directly oversee everything for Eastern US, and Allison is one of our engineers who, again, we work in tandem with. And so again, we have a nice large team. We've done more of these projects here locally and through North America than anybody else. And we look to just continue to build off that momentum. So again, thank you to everybody for their time. And hopefully we look forward to hearing from you in the future at some point.
Thanks, Chris, for that great presentation. I like the last project, of course. It seems like there's a Brazilian flag even.
It does. It does. Yep. Yep. Exactly.
And gets us back to the penguin analogy. So that's great. So I would say we are a smaller group. You guys can unmute yourself if you want to ask questions. So maybe Ben, if you want to ask your question directly to Chris, you can just unmute yourself.
So I'll just jump in real quick. Ben had asked a question about how the canopy thermal breaks compare price-wise to Armatherm's fiberglass products. Really, I would say it's tough to state that directly because we are putting together, we incorporate all of the accessory components And we are also putting together all of the calculations and stamping and sealing and owning the liability of those drawings themselves. So quite frankly, at the end of the day, all those things considered, it might even be more cost effective. But if you're just going to say, what's this fiberglass pad versus a steel product, it's going to seem slightly more expensive. Um, there's just a number of factors that go into that question. It's a bit of a loaded question. Um, and then as far as embodied carbon information for the product, we are working on that. I don't believe that we implicitly have anything thus far as it pertains to embodied carbon, but I'll have to check to see on what the latest is to that end.
And I think
Um,
the Passwords Institute is integrating the embodied carbon into the PHP as well. So it's certainly something we want to push the industry to.
Very relevant. Exactly. It's very relevant. And so we all, our standard products are 3 inches thick. We also offer 5 inch thick products, specifically for, they were created specifically for Passive House.
Mm.
So you jump from our insulation is a graphite enhanced polystyrene from BASF. It has an R value of R5 at an inch. So at 3 inches, we're at a nominal R15. At 5 inches, we're at a nominal R25. Again, it depends on the product. But to Edward's question, the standard product, the insulation's an R15. The wider product, the insulation is an R25.
So is that a variable insulation level? Let's say
Yes.
you go into a cooler, colder climate, you have a thicker insulation layer.
If the project team would like it, that's not necessarily our call to make per se. We're here to provide all pertinent, relevant options and information, for the project team ultimately, so that they can make their best informed decision of what works best for them.
Do you provide a thermal break calculation modeling? So if someone says, "Hey, I'm not 100% convinced that it's a good idea to have a thermal break
Yeah.
in the balcony," and then to
Yes.
showcase that.
Yep, we can do modeling as well.
Mm.
Absolutely. It's cumbersome, as everybody knows, so we don't get involved, being perfectly transparent, we don't get involved with it for um a heavy volume of projects. Um but yeah, we it's a service that we provide. We're happy to provide. It's another way for us to build the relationship, help further establish the relationships, whether it be new or existing.
Mm.
Um, and it's not always the designers who need convincing. Quite frankly, it's generally not the designers who need convincing. There's that cost benefit analysis, or somebody who's ultimately going to bear the burden, quote unquote, of incorporating the thermal breaks into that total estimate. And as we know, value engineering doesn't always add, it's a bit of a misnomer because it doesn't generally add value. um, but yeah, we're here to provide that service, however it may, be, whatever it may be. And that's where the DOB's inclusion of the ASHRAE coding, really calling out for thermal breaks at the areas of penetrations or non-continuity, I should say, of our building envelope has gone a very long way. So yeah, I know that, we're up on time now. But yeah, if anybody has any other questions or anything like that, whether it be now or any time down the road, please don't hesitate to reach out.
So yeah, thanks, Chris, for the great presentation. It was very, very informative, and we'll send out your contact information to everyone on the call, and then you can also watch the recording. So thanks everyone for joining, and thanks, Chris, for presenting, and thanks, Shek, for supporting us.
It's mutual. We appreciate Andreas, and we will always take you up on the opportunity. So thank you very much.